Lesson 5, this is the second demo. It starts here by saying we'll finish the problem above together. So actually the solutions are already typed out for you. And also if you want to watch the video from the first activity, you'll see me work out the whole solution there. So we're moving on to 5. It says we use our work from the previous problem to easily find f prime of 1, f prime of 4, f prime of 9 for f of x equals square root of x. So remember what we saw in the activity was that the derivative of this particular function, the square root of x function, is 1 over 2 square root of x. And so if we want to find f prime of 1, we just plug in. This is just a brand new function. You can plug in any number you want to, except for 0 in this case. I guess negatives are no good too. But we just plug in x equals 1. And we discover that the derivative at x equals 1 is a half. And that was so much fun. We'll try it at x equals 4. So that's 1 over 2 square root of 4, which is a quarter. And then lastly, at x equals 9, f prime of 9 equals 1 over 2 square root of 9, which is a sixth. And I didn't tell you this before, but in the very first, in the activity, I gave you the graph of the square root of x. So where is it? Right down here. So that function is the graph of the square root of x. I didn't share that part with you. But let's see if the calculations that we just came up with agrees with our estimating slopes of tangent lines. So we said f prime of 1 was half, and f prime of 4 was a quarter, and f prime of 6 was, f prime of 9 was a sixth. Let's see if that looks anything like what we put on the graph, the green derivative graph here. So f of 1 is a half. Here's 1, here's a half. Okay, my green thing was a little bit higher than it should have been. It's okay, it was a rough sketch. F prime of 4 is supposed to be a quarter, so at 4 we're supposed to be a quarter. Well, that's not too far off from being a quarter, I guess. And then F prime of 9 should be around a sixth. So 9 actually is one that I happen to pick. 0.2 compared to a sixth, those are pretty close to each other. Sixth is like, I think it's 0.18 repeating. So not too bad, but the nice thing about this derivative calculation is that we did the hard work to get the 1 over 2 square root of x, and then you can use it to very quickly find any derivatives you want. Number 6, here's a preview of the power rule, which gives us a shortcut to find the derivative of f of x equals x to the n. Turns out that the derivative of x to any power is, and then here's the shortcut, f prime of x equals n times x to the n minus 1. N times x to the n minus 1. So let's see if we can use that shortcut here to find the derivative of square root of x. So apparently we need the function to be written in the form x to a power. So first we need to change that square root into a power. And we all know that square root is the 1/2 power. And now let's go ahead and apply our new rule, power rule. Just sort of throwing it at you here, but let's see if we can apply it. We'll see it more formally soon. So what the power rule says is that whatever the power was, it comes right down here in the front. That's the first step. So the power is a half. So it comes right down here in the front. And then the other thing that happens is you then write an x. Okay, I can do that. X there. And then up here is n minus 1, where n was, again, the power. So you subtract 1 to get that power. So let's see if we can subtract 1 from the old power. So the old power was a half. So we subtract 1 from that and we get negative half. So that's it. That is the derivative. But let's clean it up, make it look like something we've seen before. Okay, so first of all, x to the negative 1/2. Let's make it a positive exponent and move that whole thing downstairs. So x to the negative 1/2 upstairs is the same as x to the half downstairs. We don't need a common denominator to multiply fractions. We can just multiply numerators and multiply denominators. And then x to the half on the bottom, well, let's rewrite that in radical form. X to the half is the square root of x. So 1 over 2 square root of x looks awfully familiar. In fact, it's exactly what we got here, which, remember, in the activity, we had to do a whole boatload of algebra, starting with the square root of x function to eventually get around to the derivative being 1 over 2 square root of x. So power rule is a very nifty shortcut. And again, we'll use it more formally in a coming class. Okay, number 7, the calculator can help us in a limited sense find derivatives. It can handle derivatives at a given point. So here are the here's how we do it. My operating system on this calculator is one of the older ones, so if you have one of the newer ones, it'll look a little bit more user-friendly than what I'm going to do here. Okay, so from the home screen, it says hit math and then 8. So math is right here, right below the alpha green button. Now 8 is off screen. I'm going to scroll down, but if you just hit 8, it would give it to you. So it's n deriv. Deriv is short for derivative. So I'm going to quit out of here and just show you that you can do math and then 8. And then it says, okay, you want n deriv. And now here's the syntax on my old operating system. If you have the newer operating system, make your thing look like this. So it's n deriv, then I tell it the function, second square root of x, close the parentheses to end the function, put a comma, which is above the 7. Then I put an x. This x is just the variable. It's silly. It's almost always going to be x for us, but you have to put it. It's part of the syntax. Comma, then you put the x value you want the derivative at. So if I want to know the derivative at x equals 1, which is what we calculated here in red, then I just put a 1 next. Comma 1. Close the parentheses here or not. And it says, okay, the derivative at 1 is 0.5, and then a lot of zeros, and then 625. Well, that's close, right? Look up here in red. The answer is supposed to be exactly a half. The calculator is making an error here. It's not making a huge error, but it's doing some rounding. It doesn't know that the derivative of this function is 1 over 2 square root of x. It's just trying to find the slope of a secant line, where the secant line is a very good approximation for the tangent line. Okay, you can do the same thing to find f prime of 4 and f prime of 9. So if we just do second entry, we can come back up here and just change this to a 4. We're expecting a quarter, or 0.25. Okay, that's pretty close to the right answer. And then if we do the same thing at 9, we should get right around 1/6. I think I made a mistake when I said 1/6 was around 0.18 repeating. That was silly. 1/6 is 0.16 repeating. Okay, so that's how we get the calculator to estimate derivatives at a point. Now we can actually also ask it to graph the derivative, which is the green graph that we came up with way down here. We can ask the calculator to come up with this green graph. Let's take a look at how we do that. So we're going to go into the y equals. We're going to type in the original function in y1, so that's the square root of x. And then we're going to go to y2, and it says you're going to type the following. So n deriv is still in math, and it's still number 8. And I'm going to make my syntax look like this, but if you have the newer OS, make it look like that. So I want to put y1 right here or here, and again that's vars, and then to the right, and then enter and enter. Okay, and for me it's a comma x comma. Now here's where I would normally put the number, but I don't want it to just do the derivative at a specific number. I want it to do it at a general x. Okay, and then we'll go into the window. It says here 0 to 10 is a good window, and then 0 to 3. So let's do that, and we hit graph. And the first thing it graphs is the square root function, and the second thing it's going to graph is the derivative function. And you can see the speed with which it graphs the derivative function is much lower than the speed with which it graphed the original. And that's because for every single point that it's plotting, right, every single one of these pixels that it just plotted, it is calculating very quickly the slope of a secant line, which is darn close to actually being the tangent line. So it takes some time, but it can get there. Okay, number 8, we now change gears with a new definition. A function is said to be differentiable if its derivative, which is given by this big old limit, exists. Function is differentiable if the derivative exists. Now, the derivative is fundamentally a limit, and we've seen several ways for a limit to fail to exist. Here are the basic ways for a derivative to fail to exist. So one is if you have a corner. So let's take a look at the tangent line at this point right here. So if I were to take tangent lines coming from the left side, so maybe something like this, and like this, and like this, and if I were to draw the quote-unquote last tangent line, maybe it's something like that. And the slope of that is some number, I don't know, 1. And then if I were to look at tangent lines on the right-hand side, so like that, and that, and that, and if I were to draw the last, quote-unquote, last tangent line, it's that. So maybe the slope is -1. Well, this is a real problem because what we just seen here is that the limit here, if you approach h equals 0 from above, right? If we approach from the numbers bigger than wherever this corner is, then I got a slope of -1. This limit is -1 when you're coming from above. But when you're coming from below the point, in this case, the slopes are approaching +1. And the slope here, this limit, would be +1. And we know that for a limit to exist, both two-sided limits have to exist and be equal to each other, and they aren't. And so in this case, it's no good. And so your shortcut to take away from this is if you have a corner, then the function is not differentiable there. That said, if you take a look at any other point on this graph other than the corner, the derivative exists perfectly well, right? Like I've got plenty of nice tangent lines. It's really just that one spot that's a problem. Okay, in the middle picture, it says there's a vertical tangent line. So if I look right there and I draw the tangent line, so it's saying that the tangent line is vertical, which is okay. Vertical lines are fine. But remember, the derivative is the slope of the tangent line. And what can we say about the slope of a vertical line? The slope is undefined. Undefined. And so because that slope is undefined, the derivative is not a number. It's undefined. And so the derivative does not exist at that one spot, just the one where the vertical tangent line happens. But the derivative exists perfectly well at all of these other spots. Okay, this last one is the trickiest one. We're not going to get into it, but it turns out that the derivative cannot exist if the function is discontinuous. I know that it looks like I could put a tangent line at this spot right here, and it looks like a perfectly good tangent line. It's not an undefined slope tangent line. There's not two different tangent lines depending on which direction we come from. But like I said, it's sort of a technical detail, which I'm not going to go into. But suffice it to say, if the function is discontinuous at a point, automatically it is not differentiable at the point. Okay, so let's put that new knowledge to use in number 9. Identify the points of non-differentiability of each of these functions. Okay, so this first function, you might not have seen this before, but that's called the floor function. It's just the round down function, not normal rounding, but round down. And so the derivative exists at each of these points, no problem. But then right there at the end is where the function is not continuous and therefore not differentiable. So this function here is not differentiable at -2 and -1 and 0 and 1 and 2 and forever, all the integers. Not differentiable because it's not continuous. Okay, this next middle picture here is the 5th root of x, and you can see that there's one bad spot right there at the origin. What kind of tangent line do we have there? We have a vertical tangent line. And so x equals 0 is the spot where this one is not differentiable. I'll put an x equals here. Okay, and then the last one is work for us to do. So it's a piecewise function. We'll graph the top one first. It's x when x is less than 3. So I know that the y equals x line is this 45-degree diagonal line, but it stops right before it gets to x equals 3. I guess I should say right at x equals 3, but there's a hole there. And then we'll draw the other part in purple. 2x minus 3 when x is at least 3. So I need 2 points in order to graph this line, so let's just find 2 points. Let's do f of 3 and f of 4. So if I plug 3 in for this x right here, I get 2 times 3. That's 6. Subtract 3 is 3. So that's 3 there. And then if I plug 4 in for the same x in the same bottom row, 2 times 4 is 8, minus 3 is 5. So I've got 2 points now, 3, 3, and 4, 5. So 4, 5 is here, and 3, 3, hey, it actually magically fills in that red open circle that we had before. And then we connect the dots, and so it looks like that. So that function is continuous everywhere. Why would it fail to have a derivative at some spot? Well, it's failing right here at x equals 3 because x equals 3 is a corner. The red line is not as steep as that purple line. It's not a smooth transition from one function into the other. But that function is differentiable everywhere other than x equals 3. Okay, here are some different ways to speak the language of differentiability. Differentiable at 2, at x equals 2, could be shortened to differentiable at 2. You could say some function is differentiable on an interval, for example, 0 to 5. And differentiable everywhere could be shortened to just plain differentiable. So we would say that f of x equals x squared is differentiable. meaning differentiable everywhere. Okay, so go ahead and get as far as you can on the next activity.